All right, so we're just going to go ahead and resume. If you have any questions at the end of the webinar, feel free to ask. And definitely we will be recording this session. So the first part, if you had missed it or if you were disconnected, we will provide a recording after in about 2 days.
Okay, thanks for your patience and thanks for sticking with us. Okay, so we just reviewed then the general features of our automated system, and so now I wanted to emphasize some of these features and mainly pointing out how they can benefit in the measurements that would be useful for predicting injectability. So I had mentioned that the VROC technology involves microfluidics. So the micron scales of the flow channel, that's going to imply small volume, which of course is key if you're dealing with costly samples or you're just limited in the sample that you have. Also, if you're trying to predict flow through, say, a needle or a syringe, then this can involve high shear rates. So if you're looking to determine the flow behavior, determine whether your material is Newtonian or non-Newtonian over a broad range of shear rates, then the system is going to be very useful for that, because the small volumes, or rather the small scales of the flow channel, reduce the possibility of having hydrodynamic instabilities or turbulence at high shear rates, which is a problem when you're dealing with different types of instrumentation where the length scales are much larger. Also, the system is closed, and the flow-through channel design then eliminates the presence of an air fluid interface, which you have in, say, a cone and plate rotational instrument, or any rotational instrument for that matter. So you're not going to have issues with evaporation. And just as important, if you're dealing with something such as proteins or antibodies that have hydrophobic domains that can cause them to migrate to the interface and basically form a locally higher concentration interface, this will not happen in our system because of the closed design and the lack of the air fluid interface. So there will be no artifacts due to an interfacial viscosity contribution. So your measurement, you can be confident that it's going to be a bulk viscosity and not containing this artifact due to interfacial effects. Also, because of our flow-through channel design and the ability to reverse the flow in the system, we have the feature of the sample retrieval feature. So what this means is, and we have a little graphic here that's basically showing the path forward and back, is that once the sample is tested and goes into the VROC cell, we can reverse the flow and then refill the testing syringe, so that with that single volume of sample that you've loaded, you can basically do nearly unlimited number of experiments. So you can measure over and over again with that single volume of sample. Again, and you're not going to have to worry about evaporation or any artifacts due to an interface as you measure repeatedly. And so this is just good for getting better statistics. So we have an example here of viscosity versus measurement number, likely excessive at 100 points, but you can do as much as you want to get the confidence you want. And of course, then you can do temperature sweeps, shear rate sweeps, and because of the control that's part of the instrument, you know what the sample history has been. And then we have advanced features that come with the software, both in terms of operation. So you can set up these very long, complicated protocols, the rate sweeps, temperature sweeps. And then also one of our newest features related to this instrument is, because you're generating, or you can easily generate a lot of data, we now have an analysis package that helps you work through that in a much faster way, as opposed to trying to deal with it yourself in Excel. And we won't talk a lot about clarity. We have a separate clarity information session, but I'll bring it up a little bit, because one of the features of clarity is that you can import data and do an injectability analysis using one of the equations that we're going to derive and work through here. Okay, so now that's the background on the viscosity and the instrumentation that we offer. So now let's get into trying to predict the injection force from viscosity. So when you look at the syringe, basically the injection force is you need to force the fluid through these cylindrical components in series of different diameters. And so the force to push the piston is really just going to be, you're going to have a viscous contribution because you need to force this fluid to flow, and then you're going to have a frictional component. So any friction between the barrel of the syringe and the piston. So I bring it up because that's relevant, the friction component, but as we move forward with our analysis, we're really only talking about the viscous or hydrodynamic part. So when we do a little comparison to some experimental data, we'll bring up sort of magnitudes that the frictional component may have and how that can influence the data. But for the most part, as we're moving forward, we're talking about the viscous contribution or the hydrodynamic contribution. So basically, the viscous force that you have is basically the pressure drop across the syringe times the cross-sectional area of the piston. So that's this first equation right here. So total pressure times cross-sectional area. And if you break down the syringe into different zones, you have zones 1 through 3. The barrel of the syringe, this tapered portion, and then the needle. So you have these 3 zones in series. And the way we're going to derive the force, the viscous contribution to the force, is basically by doing a force balance, which we have here. So on one end, we have the pressure drop times the cross-sectional area. So this is going to be the force you need to apply to the piston. And then this is going to be balanced by the hydrodynamic stress. And so this is going to be the viscous stress, which, as we just defined earlier, is the viscosity times the shear rate, times basically the surface area that the fluid is in contact with. So now this is going to be the circumference of the tubing times the length over which you're filling the sample with. So it's the internal area that's wetted by the fluid. And so this is what we're balancing. This is the force balance that we have. Okay, so as we discussed, we're looking at flow in a cylinder. So there's different zones in the syringe, but they're all flow inside of a circular conduit. So let's focus first on zones 1 and 3 because these are the simple uniform diameter cases. And as we go through this and we do basically a ratio of pressure drops across the different zones, in the end we don't even really address zone 2 because it's clear that the needle portion is really going to dominate. But I'm giving away my talk, so let me go ahead then. Okay, so again at the top here we have the force balance as we just discussed. And we're going to start off by looking at the case of a Newtonian fluid, because the Newtonian fluid, as you know, viscosity is independent of shear rate. It's just a constant value. And so this simplifies the fluid mechanics. And this flow in a cylindrical tube for Newtonian fluids has been worked out. The analytical solution exists, and it's basically the foundation and where we want to start. So for the Newtonian fluid flowing through a cylinder, the velocity profile, and so what we have in the tube here are basically the arrows correspond to velocity vectors. The velocity profile is parabolic. So what we're assuming then is we have no slip boundary conditions at the wall of the tubing. So velocity goes to 0 towards the wall and then maxes out in the center. And so when we're calculating the shear rate, what we're interested in is the shear rate at the wall. And that's just defined as minus the derivative velocity profile with respect to the radial position at the wall. And there's an analytical expression for this, and it's just related to the flow rate Q that you're applying to, that you're delivering the flow rate you want the fluid delivered at, divided by the radius of the cylinder. And so when we incorporate that into our force balance, and solve for pressure, now we know what the pressure drop is across any section of the tubing, just as a function of viscosity, length, flow rate, and the radius of the tubing. And so this is a well-defined law for Newtonian fluids. So let's take this and apply it specifically to the syringe. So right now we're just looking at zones 1 and 3 because these are the well-defined cylinders with uniform radius along the length. And so what we have in the table are basically some common parameters that exist for syringes and needles. And we break it down looking at in zone 1 and 3, basically fixing the radius or the diameter and the length. And what we're going to do is calculate relative magnitudes of the pressure drop using the relationship that we just derived on the previous slide. So if you go down here and you look at basically the pressure drop that occurs over the needle portion relative to the pressure drop occurring over zone 1, that just relates to length and radius of each portion. And what we can see is that the pressure drop over the needle is roughly 300,000 times that over the barrel for this set of conditions. And these are sort of representative, and this will vary slightly. But the bottom line is that the pressure drop across the needle is significantly larger than that over the other portions in the syringe. So that if we want to go forward and get an analytical expression for the injection force, then we can just assume that this pressure drop over zone 3 is going to dominate. And so we can approximate the total pressure for pressure drop over the needle portion. And then once we calculate that using the Hagen-Poiseuille law that we just derived, we can multiply it by the cross-sectional area of the piston, and then that gives us this estimate for the hydrodynamic contribution of the injection force specific to a Newtonian fluid. So to do this approximation, all you need are parameters of your syringe, the flow rate that you want to operate at, and then the viscosity of the fluid that you're going to inject. And then you can get a feel for what is the force required to force it through this syringe. So we have some examples of how the injection force can vary with some different parameters, such as the flow rate and then also the needle gauge, which then relates to the inner diameter or the radius of the needle. And what we have here are, we don't personally have our own injection force data because we don't have that instrumentation, but we found some that was presented by a group from an external company where they were measuring, they wanted Newtonian samples and they wanted to be able to control the viscosity. So they were taking various aqueous glycerol solutions, varying the volume fraction of glycerol to adjust the viscosity, and then using a compression tensile instrument to measure the injection force for their auto injectors. So this is probably likely some kind of Instron type of instrument. So what I did was I extracted the data from their presentation, and then I used the equation that we just derived for the viscous contribution. And what we're looking at then is force as a function of viscosity for either the case of a variable flow rate at a fixed needle dimensions or variable needle dimensions at a fixed flow rate. And so you can see how the injection force will vary with both viscosity and then how the rate of change will vary as you adjust these parameters. And I wanted to point out that, so if you look at the comparison of this simple expression with the data, you can see that in a number of instances we're either under predicting the force or we're at the low end of the range. And the true measurements are actually going to include the frictional component, which is not part of our prediction. And I was looking in the literature to try to find some values on what the friction is in a syringe. And of course it's going to vary. It will likely vary quite a bit depending on the materials, and then also I know that sometimes the inside of the syringe is coated to minimize the friction, so of course that will drop it then. But just as a ballpark range, I found that it's anywhere from, say, roughly 2 to 4 for glass syringes, which is what this group had used, or 2 to 6 for plastic. And like I said, I expect that could vary quite a bit, but this is just a ballpark number. So you can see that if we added that to our predictions, then that would improve the comparison and get us closer more to the mid-range of the data. So I think that if you have a separate way of estimating friction, or if you're comfortable using literature values and combining that with the viscous contribution, then this is a valuable tool to look at how changing either your formulation or the parameters of the delivery method can impact the force. Okay, so I'll use this as a moment to, I had mentioned earlier that we have recently introduced an analysis component of our software for our automated instrument. and we call this clarity. And I wanted to bring it up now at this moment because at the time for its first release, it's, as I mentioned, new. We do have an injectability analysis component, so you can import the data and then it will automatically calculate the injection force as a function of viscosity as it's presented here. And so this is just a screenshot. I didn't want to make it confusing and open up the software during the talk, but so we just have a screenshot. But you can see that it will calculate that force for you as a function of viscosity. And then down at the bottom here in the table region, there are default parameters that it initially starts for the initial calculation for the syringe parameters, but these are adjustable. So once you import the data and start the analysis, you can go in and change it to be anything you want. So there are pre-loaded diameters for different gauge needles. You can adjust barrel diameter, needle length, flow rate. This is all variable for you, and it makes it a lot easier to do the analysis because it does it for you. At the moment, the Clarity software only handles the Newtonian case, which we just talked about. So it's using that expression that we derived. Again, it's going to not be including the friction. At the moment, it does not yet have the means to handle non-Newtonian samples. That's basically a next generation implementation because there are some common shear thinning behaviors, which we'll talk about in a minute. But at this time, it's hard to predict how non-Newtonian behavior is going to be much more broad and a little more complex for the analysis. So that'll come about at a later time. But if you're dealing with Newtonian samples, or if you want to get an estimate for that, then our software can speed that up for you quite a bit. Okay. So we can talk, though, about non-Newtonian fluids and how they flow through the cylindrical channels. So if you look at, and I apologize, the presentation got shuffled a bit when we changed computers. But so reminding you that for the Newtonian case, we have the parabolic profile, the parabolic velocity profile. And we have this because in the Newtonian case, the viscosity is going to be the same across the radius of the cylinder. But because as you move from the center of the cylinder to the edge of the cylinder, you have a change in shear rate. If your material is non-Newtonian, then the viscosity response will be different as a function of radial position. And so this then tends to change the velocity profile and the shear rate at the wall, which is what's relevant for all of our calculations. So we're going to talk about shear thinning fluids because these are the most common behaviors. Shear thickening is much less common. And so what you see in the velocity profile for shear thinning fluids is it's sort of somewhat flattened out in the center, and then the rate is often higher at near the wall. So there is a general correction that you can use to correct for the shear rate at the wall. That's just going to depend on the shear rate if it were a Newtonian fluid, which we've just defined. So that's the 4q over pi r cubed. And then what you would need to know are either Q is a function of pressure drop, so flow rate is a function of pressure drop, or shear rate is a function of stress. And so you can get this from the experimental data if you have viscosity as a function of shear rate. And so then you can get the corrected shear rate at the wall. And then if we go back to our force balance, so if you recall the force balances that we had and we used to derive our viscous force, so now the cross-sectional area is the same, but what will change then is the pressure term, the pressure drop across the needle portion. And so now what you will have then is instead of a single constant viscosity times shear rate, now you'll have something that's variable. And so what you'll need to do is determine, using the correction, determine the appropriate shear rate for your experiment, for your fluid, and then use that to get the correct viscosity. And then that allows you to get the pressure drop. So it's a little bit of a process if your shear thinning is not well defined. But you can do this from experimental data. To sort of give you an idea of how this can be simplified, one of the common types of shear thinning materials is a power law fluid. So here's an example of some data that we've collected on our initium. So it's viscosity is a function of shear rate at a couple of different temperatures. And you'll see in the highlighted region, so this is a vicinity close to where you would have, where the shear rates would lie for flow through a needle. You can see that it's well characterized by power law behavior. That's the solid line. So power law is just given by this expression here, where the viscosity is some constant times shear rate to the power n-1. And as you go towards the limit of Newtonian behavior is when n goes to 1 and viscosity is just a constant. For this somewhat simple relationship, again, there's an analytical solution. So you can analytically determine the proper shear rate at the wall as a function of the power in the viscosity relationship, and then again, depending on your flow rate that you want and the radius of your needle or the gauge of your needle. So this can be determined analytically. And then we go through the same process as we went through with the Newtonian fluids, and we can derive a viscous force for a power law fluid. And so here again, all you need are the characteristics of the fluid, this constant kappa and the power law index n, and then as before, just all the parameters in terms of flow rate and syringe parameters. And you can see that this relationship in the Newtonian limit gives us the equation that we had originally. So if you have something that follows this, then again, you can use the analytical expression to get your viscous contribution. Okay, so I think we'll stop there. And what we wanted to do is sort of present the idea that you can, analyze the injectability, and you can derive force expressions that you can then use your viscosity data to predict injection force. So sometime in the future, I think if it's helpful to people, what we'll do is, now that the idea is presented and you're familiar with the equations and the theory behind it, is we'll utilize it in some more practical examples so you see how it's used and for real data. But that's where we wanted to stop today. And then we'll see if anyone has any questions. And then if you don't have questions at the moment, you can always, when you registered, you got contact information, you can always contact us and we'd be happy to get back to you and help you with any questions you might have. So thanks for joining us, and thanks for being patient when we had the technical issues.
All right, so we're having some technical difficulties overall, but thank you all for attending our webinar. If you have any immediate questions or questions that come to mind later on, again, as Stacy had mentioned, you can definitely contact the main point of contact on your email for the webinar event, but you can also contact us directly through info@riosense.com. We will be sending you a quick survey at the end of this webinar, so feel free to fill it out. We do always recommend or welcome any suggestions on webinar topics. Thank you.